So we're going to correct the voltage divider. We have the variables. Ideally, what you want to do is write down all the values. So R1 is 39K. R2, 3.9K. RC here, 10K. And RE, 1.5K. So those are the resistor values. The source voltage is 22 volts. And so the first thing we do is find out what the voltage is here across VR2. So between this point here, which is the base, and the ground. So VR2. The formula for VR2 is VCC multiplied by R2. So it's called a voltage divider. R2 over the sum of R1 plus R2. So we've got 22 multiplied by 3.9 over the sum of 3.9 plus 39. Notice I didn't put the K's. You don't need to really. Since they're all in K's, I've just put the actual numbers in and it'll still be okay. Just make sure that if there are different values like megs and K's mixed up, then it's not going to work. So if we do the math, we have 3.9, and we're going to divide by open brackets 3.9 plus 39 close brackets and multiply by 22. So we've got 2 volts. Okay, so it's going to be very similar to the one that we did before, if not almost identical. So 2 volts, that means that between this point and this point across R2, we've got 2 volts. So what I had explained before is that between this point here and this point here, we have 2 volts. So if we take the 2 volts that's here, what's in parallel with that is this diode here and RE. So to get the voltage here, which is next, RE, all we have to do is subtract this VBE, which is 0.7 volts. So VRE is VR2 minus VBE. So VR2 is 2 volts minus 0.7 is equal to 1.3. So the voltage here between these 2 terminals, the top and bottom of the resistor, is 1.3 volts. Since we have the voltage and we have the resistor value, we can get this current here. This current here is IE. So how do we get IE? VRE over the value of RE. So we have 1.3 over RE of 1.5K. $1.3 divided by 1,500. 866. 866.667 microamps. So that's IE. So that's the current right here. So if we have the current here, which is 866.667 micro, it's the same as or close to the current that's here. So once you get IE, approximately, it's the approximately the same value as IC, and this is called IC because the current's going through resistor C, or the collector. So this is also 866.667 micro. Okay. Since we have the current going through this resistor and we have the resistor value, we can find out what the voltage is across this guy here. So that's VRC. VRC is IC multiplied by RC. So the 866.66 micro. I'm just going to put in the answer. 866.66 micro multiplied by the 10K, which is 8.667 volts. So we have 8.667 volts. And we're going to write it in 8.67 volts or 667 volts. That's the voltage here. So these three components here, we have RC, we have a VRC. We have RE, we have VRE. The only other component is the collector to emitter. Okay, so we want the voltage here. The voltage here should work out to half of VCC for it to be a good amplifier. So how do we get VCE? We're going to take VCC, subtract by VRC, and subtract by VRE. So we're going to take 22. We're going to subtract by 8.667. And we're going to subtract 1.3 as well. And what we're left with is 12.003. The voltage here between collector and emitter is 12.03 volts. 12.03 volts. So 12.03 volts is approximately half of VCC. Half of VCC would have been 11 volts, so we're off by less than 10%. So it'll be a good amplifier. VRE, the last variable to solve for, is right up here. So we have 22 volts being supplied to VR1 and VR2. We already have the value for VR2. Whatever's left over will be VR1. So 22 minus 2 will give us 20 volts here. So the formula, VCC minus VR2. So looking at 20 volts.